Okay, yeah, welcome to class. This is week 10 quiz. It is basically covering, it says it covers lecture 29, but like not really. The first question is for reviewing material, where can I find an explanation to all the released quizzes? Answer, on the course website under lecture 26, we have all of the quizzes that Chi wrote up, as well as the explanations for their solutions. Oh, that was the wrong link. 29 here. So if you're having trouble understanding something we did in previous quizzes, all of the solutions are written here and everyone should have access to it. It's all public, okay? So you should answer this one. For reviewing material, where can I find explanations to the midterm exam? So again, lecture 21, when we did the midterm overview, if you guys scroll to that, we have the slides where we talk about each problem, and I tried to give you guys examples of how to work through it. And we also have the recordings on YouTube, 2 parts, okay? So yeah, if you want to study for the final and look over the midterm again, and you don't remember how you did the problems, resources are here. Okay. And then similarly, for reviewing the written portions of the homework assignments, I don't know if you guys know this, but Chi actually just posted the solutions on Blackboard and we linked to it for homework 7. So we do release the solutions on Blackboard. These are not public, so don't share them with people outside of NCAT. Don't in general, don't share the solutions too much outside of the class. Helps with future people teaching it, right? So you need to log into Blackboard first to see them. But once you're logged in, if you just click on the link, it'll take you to a PDF that has all of the questions, all the written questions, as well as a pretty long explanation of the solution. And for the coding questions, it actually includes examples of the code in the PDF. Obviously, for you guys, this is going to be different for you because everybody had a different graph. And then the last one says, I don't know if you guys knew this, but I do also release all the coding solutions on Replit after the homework is due. So for example, homework 7 code solution, if you click on this link, it'll actually take you to a Replit for C++. I also do the Python ones that has an answer for the answers.cpp. So this one might not be that helpful. So these parts won't be that helpful because everybody's graph is different. But if you were like, oh, I don't remember how does build graph work? The code is here. And then what I try to do is on the written solutions, I try to explain why the algorithm works a certain way. But yeah, so again, this should be a free 100, but also in general, there should be no excuse. If you have the time, you should be able to submit homework corrections, right? I give you all the resources and you should try to learn that material. Does that make sense? Cool. All right, let's jump into lecture because we have a ton of stuff to cover today. I'm really excited. You guys excited? Yeah, everybody's super happy. Yeah, this is my core group. I really appreciate you guys still coming. We used to have a group that used to come in that corner. I don't know what happened to them. They were pretty consistent for most of the semester. But yeah, now they're not coming anymore. So I'll try to reach out to them. All right. Homework 8 is due today. Yeah. Oh, the auto grader is broken or something.
Professor, can you hear me?
Yeah. Oh, I see. Well, thankfully, we do have a homework party today, right after lecture. So if you want to come hang out with me, you can come hang out with me. If you want to just ask me questions, you can ask me questions. I don't know. Has anybody else tried submitting the auto grader and been it's not working?
Professor.
You had issues as well? Okay. It might be the auto grader. I will try to fix it during the homework party, I guess. Yeah, when you guys run into this, if you post on Piazza or email me, then I can try to fix it. I'm not sure what might be wrong with it, but I'll take a look. Cool. Also, they asked me to remind you guys, there's an end of semester course evaluation survey on Blackboard for the school. This is actually not related to Meta, but they want me to tell you guys to fill it out. So one thing I was thinking about is trying to give bonus points. Oh, Leander, no, I cannot hear you. Hello?
Can you hear me now? Test.
Oh, yes, offer bonus points. So, okay, if I do offer, let's say like 1% for the class, the way I don't know who submits and who doesn't submit. So the proposal is if we can get X% of the entire class to submit it, then everyone gets 1% bonus point for their final grade. Thoughts? Well, yeah, what do you guys suggest for the X? 50%? You guys have like such low expectations on your.
I mean, to be honest, the class, like, actually here, like, what percentage of the class is here right now? So who's really gonna?
Yeah, but but there's folks on Zoom, right? So there's at least 20 people here, and then there's I think there's 20-ish on Zoom, so that's 40.
I don't really have.
I'm gonna say 80%, and you get 1% bonus if you can get 80% of the class to fill it out. If you get 100% of the class to fill it out, I'll give you 3 bonus points.
That's not.
No?
We got one person. Yeah, it's not gonna happen. But
I'll bump everybody's grade by, no, I'm kidding. I can't do that because that's unfair to the people that are already going to get an A+ or like an A, right? So, okay, so I will fill this in. Thank you. Let's do, okay, I'll fill it in later because my laptop is being hella slow. So 80% is the goal. If you guys get it, everybody gets 1%. Okay, cool. All right, so today we're going to cover minimal spanning trees. So now we're actually starting the content, and we have a lot of really cool stuff. The goal is to cover 2 different algorithms today for minimal spanning trees. All right, so let's get excited. This is from last lecture. I'm going to skip. You guys are not responsible for knowing Huffman trees anymore. Okay, we just don't have time to cover them. So I have the slides if you guys want to look at it on your own time, but you are not responsible for Huffman trees. So I'm just going to skip this. But by the way, the general idea is you have a bunch of nodes that tell you for each letter how frequent it occurs. And then what you do is you build a tree by merging the 2 nodes that are the least frequent into a new node. That has the sum of the frequencies, its frequency, and then you keep doing this, and then eventually that gives you a tree, and then the left edge is a 0 and the right edge is a 1, and that gives you the code for that letter. So we're not going to cover this in too much detail. You're not responsible for knowing it, but if you're interested in Huffman and coding, you can look it up on your own time. Okay. Yes, it does work. More skip. Okay, today we're going to cover a greedy algorithm for something called the minimum spanning tree, which is a very interesting concept. So first, I'm going to tell you what a minimum spanning tree. Then we're going to do a little introduction to some graph theory like definitions, basically some definitions that we're going to use in proving that our algorithm works. And then we're going to cover Prim's algorithm, which is an algorithm to give you a minimum spanning tree. And then we're going to cover Kruskal's algorithm, which is also another algorithm to give you a minimum spanning tree. And that's it. Okay, so that's the agenda for today. You are responsible for knowing how these 2 algorithms work, Prim's and Kruskal's. Cool. Any questions so far? Okay, so minimum spanning tree. Here is a connected graph. Okay, this works for directed graphs as well, but here's an undirected and fully connected graph. Okay, undirected weight graph. Here's a definition. A spanning tree is a tree that connects all the vertices. So what's a tree? A tree is a graph with no cycles. Okay, a tree is a graph that has n-1 edges. So if it connects n nodes, it has n-1 edges. Okay, a spanning tree is going to be a tree of this graph that connects all the nodes. Do you guys see I mean, I'm going to show you an example, but this is a spanning tree, for example. So if you take these edges, of which, so there are 1, 2, I think there's 8 nodes, 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's 9 nodes. So you'll notice that these edges are 8, 1, 2, 3, 4, 5, 6, 7, 8. And they connect all of the nodes. So you can get from A to any node just on these edges. Okay, that is a spanning tree, right? For any graph that is connected, there is a spanning tree. Cool. The cost of the spanning tree is you add up all the edges that you're using in your tree, right? So you can imagine there's other trees that also span, right? Like I could not take this edge and maybe take this edge, right? That is also a spanning tree, right? And each tree has a cost associated with it, which is the sum of each of the edge weights in the tree, okay? Right, so this is a spanning tree. It has cost 67. So if you add up all the numbers for the edges it took in, it was cost 67. This is another tree, all right? So it's still spanning. It is still a tree because it still connects everything. So like from H, you can get to A, like by going this way, right? But this tree has lower cost. It has cost 37. And actually, this is the minimal spanning tree of this graph. This is the spanning tree with the least cost, with the lowest cost. Right. So a minimum spanning tree is a tree of minimum cost. So now you guys know what a minimum spanning tree is. Minimum spanning trees are actually really useful, like in the real world. So they were actually originally discovered. So the algorithms we're going to talk about were actually, a mathematician discovered it in the 1930s. So it's actually a very old algorithm for one of them. They were rediscovered in the 1960s by Dijkstra, who you guys know of Dijkstra's algorithm fame, and by Prim, who you guys will now know of Prim's algorithm fame. But the original algorithm was actually discovered to create these trees was discovered in the 1930s. And the reason was they were trying to figure out if I want to connect homes or houses to the electricity network, right? So all of those places can be nodes. And you can imagine you can always connect any 2 houses together, right? For some amount of money, right? Like if it goes under a building, it's going to cost you more. If it is, they're very close to each other, it's going to cost you less, right? So what they were trying to figure out is like, what is the cheapest network I can build that will be the minimum cost, but still connects everybody that I want to connect. Cool. They're also very useful in genetic distance for cluster analysis, image processing, and the other thing is minimal spanning trees are often used for more advanced algorithms. So they'll say like, as step 1, let's find a minimal spanning tree of this graph, and they'll do something else. Okay. It's actually pretty cool. You guys can you guys imagine why it would be useful to have a minimal spanning tree for like building out electricity, or like when somebody's like trying to connect like all of the fiber optic cables for laying out network, right? Yeah, cool. So the goal of the class is how do we find a minimal spanning tree? We're going to see 2 greedy algorithms. So we're still in the greedy section. Turns out both of these algorithms are greedy. And in order to prove that the greedy algorithms work, we're going to show this. Suppose that our choices so far are consistent with an MST. So assume that all of the edges we have picked to be in our MST are part of a minimal spanning tree. Okay. Then the next choice you make will still be part of some minimal spanning tree. And that's how we're going to prove, because all of the algorithms, the way they work is they pick an edge and they pick it greedily. And then that's how they build up the tree. So who wants to brainstorm some greedy algorithms? So let's say I gave you this problem and I told you, I am going to give you a graph with some edges, and each edge is going to have a weight. And I want you to find a minimal spanning tree of this graph. And I'm telling you, there is a greedy algorithm that works. Any ideas? You're trying to find, basically, you're trying to find a set of n-1 edges that connect all of the nodes and have the lowest cost. Yeah, Jonathan?
You just constantly choose like the edge that's the lower cost. Like you go from A to B with 4, you go from B to C with 8, you go C to I, and then I to G, G to H, and then you have a thing between G and F.
So you're starting at 4 and you're saying I need to connect 4 to something and the cheapest edge is 4, so I'm going to take the 4 one. Okay. And then you're saying B, I need to connect you to something and the cheapest edge is actually 8, so I'm actually going to take 8. That is Prim's algorithm. Yes, that works. And that is correct. Any other greedy algorithms? So you have just discovered Prim's algorithm. Somebody discovered in the 60s, you're a little bit late on it, but good work. Any other suggestions for a greedy algorithm? So he said, I'm going to start with a node, and then out of each node, I'm going to take the cheapest edge that connects me to stuff I'm not already connected to. Okay. What's another greedy algorithm, you think? So what if I don't start with a node? What would be like the greediest thing to do? If you're like, I just want to find, a tree which consists of edges that has the minimum cost, what would be like? Somebody else? Yeah. Starting with the lowest edge, and that is Kruskal's algorithm, which he discovered a few years after Prim. So good work. So the algorithm, that one, the way it works is you look at all your edges, you sort them, and you arbitrarily take the cheapest one. That edge is now part of your MST. It is going to connect some nodes. Then you take the next cheapest one, which is going to be this term. So we're going to walk through both of these, but you guys have now discovered both of the algorithms. So you now know the idea. Now the question is, how do you actually implement it and how fast are they? Okay. So before we get to that, a brief aside, this is going to be helpful for us. There is something, this is graph theory. So if you guys are interested in this and you're interested in taking more computer science classes, you would look into the graph theory section. So there's something in graphs called cuts. That's like, we're going to define it. It's a cut in a graph. This is a cut, okay? This is the cut of A, B, D, E, and H, I, C, G, F. Yeah.
Would that mess up like how much weight is on the lines that you cut in the graph?
We are going to talk about how much weight is in the graph in the ones that are cut, but I'm introducing a concept called a cut. So a cut is a partition of the vertices. So you're going to split them into two sets, set 1 and set B. That's all a cut is you are taking a graph and you're going to split it into two sets. One way to visualize it is you can imagine drawing a line. And then you'll notice that for every cut, there's going to be some edges that respect the cut, which means the cut doesn't cut them, right? Like they're still around. And there's going to be some edges that get cut by the cut, that go through the cut. Okay. So this is also a valid cut because you just have to have two sets of vertices. B, C, E, G, H are here, and E are going to be considered in the same set. And then the rest of them are another set. So it's just take your vertices, split them into two groups. That is going to define a cut for your graph. There's going to be edges that go across the group, and there's going to be edges within the groups. Okay. This is not a cut. Why is this not a cut? It doesn't separate anything from anything else. So like F is still part, like it's still connected to C, which is supposed to be in the other group, right? Okay, so let S be a set of edges in G. So consider any set of edges. We say that the cut respects S if no edges in S cross the cut. Okay. So for any set of edges, you can ask the question, does this set respect a particular cut? And it does respect it as long as the edges don't cross the cut. Again, these are all just definitions that we're going to use for our proof. Okay. An edge that crosses the cut called light if it has the smallest weight of any edge that crosses the cut. So for this example, where's my light edge?
You said that the smallest.
That has the smallest weight of any edge that crosses the cut. Which one?
You said C to D.
Yes, C to D. Why? Yes, because its weight is 7. The other ones that cross are F to E, which has weight 10, D to F, which has weight 14, B to C, which has 8, B to H, which has 11, and A to H, which has 8. So all of those cross the cut, but the smallest one is 7. So that's considered our light edge. Okay. Again, these are all just definitions. If you're interested in how these definitions play with each other, then you're looking at graph theory. Okay, so here is the lemma, and this is why all of our algorithms work. So both prims and Kruskal's work because of this. So let S be the set of edges and consider a cut that respects S. So S is going to be the set of edges we have taken into our MST so far, right? Now consider a cut that respects S. What does that mean? That means consider a cut of the graph where all the vertices that are connected by our set S are on one side and all the vertices are on another side. Now, suppose there's a minimal spanning tree that has S. So the edges in S are part of the minimal spanning tree. So there could be more edges to get to the full tree, right? But the edges in S are going to be part of a minimal spanning tree. Then suppose we have a light edge UV. So there is going to be some edge that crosses the cut, and there is going to be some minimum edge, right? Then the claim is that there is going to be a minimal spanning tree that contains the set S plus our edge UV. So the claim is I can add the edge UV to my set S, and that will still be a minimal spanning, like it'll still go towards building a minimal spanning tree. Yeah.
The tree that you currently have, those yellow ones, the yellow.
Yeah, so the yellow ones are S, but this is not a complete tree. Like it's not complete yet. It's just S is just 1, 2, 3, 4, 5 edges, right? A tree for this graph needs to have 8 edges because there's 9 nodes. But we're saying, suppose you have some edges already that your algorithm has picked. Now, there is an MST that contains S. There is some tree that is going to have these edges, right? Or suppose there's a tree that has these edges. Then there is also a cut that respects those edges, which means they're all on one side. There is no yellow edge that is crossing the cut. There is some, this is not the only cut that does that. There are other cuts that do it, but there's some cut. Now for that cut, there is going to be a minimum edge that crosses the cut. What this is saying is it's saying, I can add this edge to my set S, and this will also be part of a minimal spanning tree. So assume these are already part of a minimal spanning tree. Then I can add the light edge, and it will also be part of a minimal spanning tree. Yeah. The purpose of the cut is to define the light edge. Because you need a cut for the, like you need, so basically what we're saying is like, if we take the vertices that we have already connected and the vertices that we have not connected, they are, that forms the cut, that forms a partition of 2 vertices. There is going to be some edge between those vertices that is the cheapest. That edge is part of our MST. That's the claim. I have not proven it to you, but that is the claim. Okay. And because of that, the algorithm that always picks the smallest edge, you can imagine at the beginning, I have all my vertices on one side, and then that edge I pick, which is the smallest, is going to cross some cut that connects one vertex to everything else. And because it's the cheapest, by this lemma, that edge is part of an MST. And then similarly for the algorithm, when you guys, let's consider A, and let me try to connect it, right? If I have A, there's a cut here. By this lemma, the cut with the cheapest, the light edge of that cut is in an MST. So my greedy algorithm takes that. And that's why both of the greedy algorithms actually work. They do give you the minimal spanning tree. Cool. Yeah, so that's what we were saying. So like, it is safe to add this edge. Okay. So here's the proof of the lemma. Assume that we have a cut that respects S. Assume that S is part of some MST. So these are all the assumptions that we made. Say that UV is light. So it is the one that has the lowest cost crossing the edge, right? If this edge is in my MST that I'm thinking about, if it's in the solution, I'm done. Like it's okay to pick it because it's in the solution, right? So the tricky part is, let's suppose it is not in the solution that I'm thinking about. Let's say I'm thinking of a different minimal spanning tree that does not have this edge, right? Then note that if I add the edge UV to T, it'll make a cycle. Why? Okay, this slide is better. Let's get to this one. So let's say UV is my light edge, right? And what I'm saying is my greedy algorithm wants to take it. We want to take that edge, but it is not in the MST that we were thinking about at the beginning. So it is not in a minimal spanning tree, right? However, a minimal spanning tree has to connect all of the nodes. So there is some other edge in the minimal spanning tree that crosses the cut. Otherwise, the nodes wouldn't be connected, right? So there is some other edge, not this one. There's some other edge that crosses the cut, okay? However, that's going to create a cycle. Because now I have a tree with n, I have a graph with n edges. So it is not right. So in my minimal spanning tree, if I add UV to it, it's actually going to create a cycle and go back to the original set of nodes. So if you consider swapping this edge with this edge, the new tree that you create by swapping those edges can only be cheaper than the original tree you were thinking of. But the original tree you were thinking of was minimal. Therefore, the new tree you created is also minimal because it cannot get any cheaper than the best. Okay. So again, consider swapping UV. So this is the light edge of the cut for XY, which is some other edge. Because these edges are both part of the cut, you know this edge has to be cheaper than this edge. Cannot be more expensive because this is the light one, right? But the way we picked it is it was the cheapest crossing the cut. So if you swap them and now you add this edge to the tree instead of this one, you still have a spanning tree because everything is still connected, okay? But the new tree is going to be cheaper than the tree you started with, but it can't be cheaper because the tree you started with was minimal spanning. And that's it. That is the proof. Okay. So you guys should think about this, like it is still a spanning tree because everything is still connected. I'm only considering these two edges. When I added the edge, it created a cycle. So I can remove any edge from the cycle and everything is still connected because they're undirected edges. And it cannot have a cost that's more than T. And T is minimal. So the new tree is also minimal. So T prime is an MST. It is a minimal spanning tree containing S and UV. So if our light edge was in the tree we were thinking about originally, then we're done. If it was not in the tree we were thinking about, we can create a tree that is still minimal that has our light edge. Therefore, if our algorithm only picks light edges, it will be correct. Cool. That is the lemma, and we have proven it. It might take, I don't know. Do you guys, how do you guys feel about the proof? Not really, not too good. Yeah, question?
side to another side, but it says that there's a side.
Oh, on the like, there is, so this is like this proof can be made more formal. So this part of like, it still has a spanning tree. It should make sense to you, like why it is still a spanning tree when I swap the edges. But you should also be like, anytime you see somebody trying to prove you something, you should be like, oh, you should write all this down like mathematically and like have all the logical, like this is not a very like thorough proof, I would say. This is just trying to give you the idea of why the tree is still minimal. Okay, that is the end. If you understood that, then you understand why the algorithms work. If you did not understand that, you don't need to, because I'm going to tell you the algorithms and they do work, but you know, it kind of sucks if you just know the algorithm but don't understand why it works. All right, so back to minimal spanning trees. How do we find one? We're going to see two greedy algorithms. So the strategy is we're going to make a series of choices to add edges to the tree, and we're going to show that each edge we add is safe to add. And by our lemma, by the theorem we prove, because each edge is safe, then it is a minimal spanning tree. Cool. Yeah. So here are the algorithms. So like you guys said, who reinvented prims? Was that you? Okay, Jonathan. So this was Jonathan's suggestion for an algorithm, and this works. So good work. You start at A. What edge do I pick?
You go A to B, 4.
Yeah, so you first go to 4. Why is that edge in an MST? Why do you know that it must be part of a minimal spanning tree? Because this is the cut you're thinking about. You're thinking of A and everything else, right? I don't have any edges in S right now, so actually S is empty. But by our lemma, the minimal tree, the light edge in this cut, which is 4, is going to be in some minimal spanning tree. So we can take it. Okay. Oh, I did it. I started with H. I'm sorry. Sorry, I started with H. Okay, so I started here with H. So you're considering this cut. So what edge do you take? Yeah, you take 1. Okay. Now, if you continue the algorithm, you are now considering what cut? You're considering this cut because these are connected. So now these are part of one side, H and G. Now, what edge do you take? Now you take 2 because it is safe to take, right? So after you take 2, you are now considering this cut. Now, what edge is safe to take in this cut? Yep. So you take 4, and now you are considering this cut. So which edge is safe to take now? Do you guys see how the algorithm is working and why it works? Because every time we're implicitly considering these cuts and we're only ever taking the light edge. So if you believe the lemma, then this edge is always part of an MST. Okay. So you take 2. So I'll just keep going. You take 2. What edge do you take next? Yes, you take 7. What do I take next? All right, somebody other than Jonathan? Yeah.
Like the cut are very safe from going back to a node that's already been to, right?
The cut is, we don't actually use the cut in the algorithm. It is more, we think about the cut to help us understand why picking this edge is still in an MST. But in the algorithm itself, we don't really explicitly talk about the cut. We just talk about like, what are all the ways that we can currently reach a node that is not currently connected to us. Yeah.
How do you know when to stop finding the light?
How do you know? How do you know when you finish the tree? When you have n-1 edges. So once you've done it n-1 times, you are done. So wait, yeah. So what's the next edge? Yeah. Question. Or. Yep. 8. Then you do 4. Great. Then you do 9. Great. And then. and then you're done. Everything is now connected, right? There is, if you consider all the nodes that are connected, it's all of them. So now your cut is like the whole graph, and then like something outside the graph, right? Cool. That is the algorithm. This was originally discovered by a mathematician, it turns out, back in the 1930s. He was Czech. His name is Jarnik. He was never given credit for his discovery because somebody rediscovered it in the US, Prim, while doing research, I think, at Bell Labs. So that is why it is currently known as Prim's algorithm, but people are now proposing calling it the Jarnik-Prim-Dijkstra algorithm because you want to give credit to everyone. And then Dijkstra also rediscovered it in 1959 when he was discovering the Dijkstra shortest path algorithm. Cool. So here's the pseudocode. So you're given a graph G and some starting vertex S. You can actually start at any vertex. It may give you different trees depending on which vertex you start. They're all minimal. So another way, like another reason why greedy algorithms sort of work is that generally there are a lot of answers that are all correct. And the greedy algorithms are like, as long as I still have some answer that I have not ruled out, eventually I'll get a right answer. So the first thing you do is you let SU be the lightest edge coming out of S. So this is where we started with H. You consider all the edges coming out of H. Take SU to be the lightest one, the cheapest one. Then your minimal spanning tree starts with SU. So it's going to have that edge in it. That's it. Now you consider the vertices you've visited. So you have already visited S and U, right? And while the vertices you've visited is less than the size of the graph, so it's less than or equal to n-1, right? We find the lightest edge, xv, in the graph such that x is part of our visited vertices and v is not. So this is an edge crossing the cut, right? Then we add that edge to the MST. We add v to visited. So we add it to the ones we have already been to. And then at the end, once we're done with this while loop, we return the MST. So this is the algorithm that we walked through. This is the algorithm you guys described. This is a very slow algorithm. Who can try to estimate the running time? Somebody that's not Jonathan. I wonder if there's somebody on Zoom. There's 20 people on Zoom, but they're not speaking up. No? Anybody else? All right, Jonathan, give it a shot. What did you want to say for the running time? Why? Well, you've got a loop, so you're close. So this is at least O of n. Why? So the loop is at least n times. Why? Because each time you go through the loop, you add a vertex that you have not visited to the visited. So at most, you're going to add n vertices, right? And then you're done. So the loop alone is O of n, right? Now, this, and this turns out to be, so these two are constant, obviously. Let SU be the lightest edge coming out of S. That could be O of m, because it depends on how many edges are coming out of S, right? So at least you've got O of m here, O of 1 here, O of 1 here. The while loop alone is O of n, and that's, O of n times O of whatever is inside, right? So again, finding the lightest edge in E, what is like the, not necessarily the dumbest way, but what is like a way you can try to do it? Go through
Can you
all
hear
the
me?
edges, right? And check, is one side in X, is the other side in B, right? So at minimum, you're like, this is O of m, right? I'm going to say these are constant, but they're not worse than O of m, let's say that. So what is the running time then? O of n m. Yeah, that's really bad because m can be what? N squared. So the running time is O of n cubed. Okay. So this algorithm is actually not very good. It does work. Wow, I just never have enough time. I guess we're gonna do Kruskal's on Wednesday. That's all right. We like Kruskal's. Kruskal's algorithm is actually simpler. But anyway, does it work? Yes, this does work because of the lemma again. The pseudocode I give you is called slow prim for a reason. There is a better way to implement this. Can you guys, what does this algorithm remind you of? Another algorithm that we covered in class. This idea of like, I start at a vertex and then I like pick one of the edges. And then out of all the edges that are still going out, I like pick another one. And then, yeah, Dijkstra, yeah. So you can imagine that's why Dijkstra also discovered this algorithm. They're very, very similar. And if you use the implementation of Dijkstra, they actually have the same running time. So the thing with Dijkstra is, let's skip the, does it work is because of the lemma. So we kind of talked about that already. So I'm going to skip. Okay. How do you actually implement this? So let's walk through an example. Oh, man, my graph is bad. Okay. So this is how you efficiently implement it. So we're just going to finish prims today. We're going to do Kruskal next lecture. Okay. So an efficient implementation is you have for every vertex, you're going to have a key. So you're going to have a value associated with it. So in Dijkstra, this is the D array, right? Every vertex has a overestimate for the distance. Now we're also similarly going to have an array. We're going to call it K for key, where every node is going to have an estimate of how far it is from the tree you're currently growing. So it's not exactly the same as Dijkstra, but it is very similar. And it's also going to have a parent telling you like, where did you come from? Where did that estimate come from? So in Dijkstra, this was the Prev array. We're also going to call it Prev here, I think. So until all the vertices are reached. Oh, great. There's the graph. All right. So this is where you start out. So your A. So now we're going to do it from A. It's going to start with a key estimate of 0. And then everything else is going to start with infinity, right? What you do first, you activate some unreached vertex with the smallest key. So this is the same thing as Dijkstra, right? You look at all the ones you have not finished yet in the D array, and you take the one with the smallest estimate. That's the one you're going to go to next. Same thing with prims. Then for each of the neighbors of that node, you're going to do an update. If my estimate is better by taking that edge, the new edge, UV, then I will update that value. What is different from Dijkstra? What does Dijkstra do here that's different? Other than the fact that Dijkstra has like a D here, a D here. What is Dijkstra's thing here instead of just the weight of the edge? It has to do with the shortest path. So how do you calculate the estimate for the path in Dijkstra? Yes, you first have to get to U. So Dijkstra does du plus then the weight of the edge, right? That is the only difference. The algorithms are otherwise exactly the same. But you get to write 2 different papers for the algorithms. Anyway, they're exactly the same otherwise. So they are exactly the same otherwise. They behave very differently though. There is no reason to believe that the edges you pick here have anything to do with shortest paths. Well, they might have something to do. I don't know. Actually, we should think about that. But like, there's no reason to believe that. This is the only difference. So what is the running time of this improved version of the algorithm? This is one of those things where it's a little harder to like think about it, and it's easier if you just remember what Dijkstra's running time is. O of n log m is correct. Yes. How do I know it's correct? I just remember that's Dijkstra's. Okay. We have an example. I guess I'll walk through the example. So we'll see how it works, right? So this is what we're going to do. We start with A. This is another example. the first thing you do is you look at all the neighbors and you update the parents. So the arrow represents updating the parents, but in code, that means that's this part, update, prev v equals u. So you're telling me where you came from. And then I also update the distances, right? Not the distances, the keys. So this time it's not distances. So these get 4 and 8, right? Now the interesting thing is this part, right? So you want to activate the unreached vertex u with the smallest key. The way Dijkstra does that is it keeps a min heap, right? That's how we got a really good running time, because otherwise you have to like iterate over D and find the smallest one. But if you keep a min heap, it actually does it in log m time, which is the same as log n, it turns out, if you work it out, because log m is log n squared, and then the 2 comes out as a constant. But it'll pick 4 because it's the smallest one. So then it goes to B, and then you just repeat. So you look for every neighbor and you update the previous, and then you also update the estimates. So notice that this is not cheaper. 8 is already pretty big. So this we don't update. But these two, infinity and 8, you take 8, infinity and 11, you take 11. Right? Then you add, so now you're at this part, you add PU to U. So you add this edge to your MST. What do I do next? So I just finished this part where I marked B as reached, and I added PU U to the MST. So I added the parent of B, the edge from the parent of B to B to my MST. So now I am back to this. Yeah, Isaiah. Not the smallest edge. You take the smallest estimate. So out of all the estimates you have, so 0, well, 4, these are done. So out of 8, 8, and 11, you take the smallest one. By definition, we're going to go to C first, because why not? Now I look at all of C's neighbors and I update their estimates, right? So this actually gets updated to 2, this gets updated to 4, this gets updated to 7, right? And you can see that like this is basically keeping track of our cut, and it's adding new, yeah. It would, if you went to H instead of C, it would give you a different tree, I think. Yes, because it'll end up taking like, yeah, it'll give you a very different tree, actually, I think. It will, yes, it will always be the minimal spanning tree. Yes, because as long as you're considering some cut and you're taking the light edge, you will always get an MST. So in a way, there are many minimal spanning trees in graphs. Yeah.
How do you figure out the estimate after you reach the number?
You just update either the previous estimate or the weight of the edge it took you to get there. That's it. Yeah, so it's actually a little, I mean, you could say it's a little simpler than Dijkstra. Dijkstra has the like KU plus weight, right? And then all of this would be like this weight stuff, all of this, you would update in your data structure. So there's like a update key for heaps. Yeah. Oh, okay. So we are at time. That is the entirety. This is so the good implementation of this algorithm is look up Dijkstra's implementation and tweak it a little bit. Okay. Now, the last thing you want to remember is that the running time for Dijkstra yeah, so the running time is n log n. So it is m log n if you just use the red black tree, because you have to go through all m edges, right? But if you use something called the Fibonacci keep, which we did not cover, it's a more advanced data structure, but we did talk about it during Dijkstra, the running time becomes m plus n log n. And this is actually one of the faster implementations that we know of. All right. Thanks for coming, folks, on Zoom, and I will see you guys on Wednesday to finish up Kruskal's algorithm, which is actually a lot simpler, but also more interesting. Anyway. Leander, yes, the errors I found is that the grader does not work well when you're creating a vector for question 0. For inserting information into the map of question 3. Okay, I will, all right, yeah, so the auto grader is a little off, I guess. I will try to take a look at that right after lecture. Yeah. Thanks, Leander.